sklearn, base, Regressor Mixin. Description: Regressor Mixin is a base class in scikit-learn sklearn that defines the common interface for regression models. It provides a set of methods and attributes that all regression models in sklearn should implement. This class acts as a blueprint for building regression models, ensuring consistency and interoperability within the sklearn ecosystem. Inputs: training data. This includes the features independent variables used to predict the target variable. The features can be represented as a NumPy array or a pandas data frame. Target variable: this is the variable that the model aims to predict. It should be a NumPy array or a pandas series. Outputs: trained model. After fitting the model with training data, the Regressor Mixin object itself represents the trained model, ready to make predictions. Predictions when given new input data features. The trained model can generate predictions for the target variable. These predictions are typically in the form of a NumPy array. Steps: initialization. The Regressor Mixin class is typically inherited by specific regression models, like linear regression, decision tree regressor, etc. When initializing these models, you might configure certain parameters like regularization strength, tree depth, etc. Fitting the .fit method is called on the model with training data features and target variable. This step trains the model by learning the relationships between features and the target. Prediction: once trained, the predict method can be used to generate predictions on new input data. The model takes the features as input and outputs predicted values for the target variable. Metrics: mean squared error. MSE calculates the average squared difference between actual values and predicted values. Root: mean squared error. RMSE, the square root of MSE, providing a measure of error in the same units as the target variable. Mean absolute error may computes the average absolute difference between actual and predicted values. R squared represents the proportion of variance in the target variable explained by the model. Visualization plots: scatter plot of actual vs predicted values helps visualize the model's performance and identify potential biases or outliers. Residual plot displays the difference between actual and predicted values, revealing patterns in the model's errors. Fine-tune parameters: regularization strength, e.g., L1, L2 controls the complexity of the model and helps prevent overfitting. Tree depth: for tree-based models limits the depth of the decision tree, reducing complexity and preventing overfitting. Learning rate: for gradient-based models controls the step size during optimization, influencing the speed and stability of training. Uncertainty methods: confidence intervals provide a range around the prediction, indicating the model's uncertainty. Prediction intervals extend confidence intervals to account for both model uncertainty and randomness in the data. Challenges and fixes: Challenge 1: overfitting. The model performs well on the training data but generalizes poorly to unseen data. Sample use case that resulted in challenge 1: a model trained on a small data set might learn specific patterns in the training data that are not representative of the wider population. Fixes to challenge 1: regularization techniques. L1, L2 penalize complex models, reducing overfitting. Cross-validation: split the training data into folds, train on different folds, and evaluate on the remaining fold to assess generalization performance. Challenge 2: underfitting. The model is too simple and cannot capture the underlying patterns in the data. Sample use case that resulted in challenge 2: a linear model might fail to capture nonlinear relationships in the data. Fixes to challenge 2: Increase model complexity. Explore more complex models like polynomial regression or decision trees. Feature engineering. Create new features that might capture the nonlinear relationships in the data. Hyperparameter tuning. Optimize parameters like tree depth or regularization strength to find the best fit for the data. Challenge 3. Data leakage. Information from the target variable is unintentionally included in the features, leading to overly optimistic performance. Sample use case that resulted in challenge 3 using a feature that is derived from the target variable for training. Fixes to challenge 3. Careful feature selection. Ensure that features used for training do not directly depend on or contain information about the target variable. Data preprocessing. Remove any potential leakage sources from the data before training. Challenge 4. Multicollinearity. High correlation between features can make it difficult for the model to determine the individual effects of each feature. Sample use case that resulted in challenge 4. 2 features that measure similar aspects of the data may be highly correlated. Fixes to challenge 4. Feature selection. Choose a subset of features that are not highly correlated. Regularization techniques penalize models that rely heavily on highly correlated features.